Okay, so imagine there is an object. Now this object is, let me just take a rectangular cuboid so that way it's easier to visualize x, y, z. And this thing can, it can spin about its axis. And then it can also, well, translate along the x, y, z axis. So there is gravity, and then you throw the object in the air with a certain spin and certain x, y, z velocity. What is the motion of this block? So given an initial speed, so let's say linear speed, and angular speed, describe the motion of the object. In other words, what we'll do is we'll derive the equations. Okay, and you'll see that at some point of time, we are better off using MATLAB to derive. Then we'll simulate the system once we have the equations using an integrator. And then finally we'll animate the motion. Okay, so this is sort of the build up towards quadcopter. We need to do 3D dynamics in order to do that. So what we'll do is we'll use the Euler-Lagrange method to derive the equations of motion using Euler-Lagrange method. Okay, so the good thing about Euler-Lagrange is it's easy to build go from 2D to 3D once we have figured out the kinematic. So the first step, if you recollect, for Euler-Lagrange is to write the position of the center of mass. In this case, it's simply the x, y, z, right? That's the x. So let's say that this is the center of mass, which is also at the geometric center. And that's really simple. That's not much to be done there. Then we also need the angular position. And then what we're going to do is, for the angular position, which we did not have for, we had only theta for say a 2-link manipulator or a 1-link manipulator, but for this one we have all 3 rotations. So let's just use the Euler 3-to-1 rotation. So 3-to-1, which is basically phi about, let's say psi about z, then we have theta about y, and then we have phi about x. So let's just write it that way. So that's nothing to be done there. We also need to write the velocities, right? So velocities are simply x dot, y dot, z dot. There's nothing much to be done there. And then the angular velocity, which is where we need to know the relation between angular velocity and Euler angular rate. So what we'll do is we'll actually use the body frame, and why I'm using body frame will be clear a little bit later. So we wrote down the formula for the, actually we derived a formula for the angular velocity in body frame. It's basically 1, 0, 0, 0 cosine of phi minus sine of phi, and then minus sine theta cosine theta sine of phi cosine of theta cosine of phi times the 3 rates, phi dot, theta dot, psi dot. So this was derived in the last class. Okay, and that's needed because the angular speed is not the same as the Euler rates. There is a relation which we derived last time. So we have the positions and velocities. The next step in Euler-Lagrange method is to write the kinetic energy. And so we'll do that next. So step 2 is write the kinetic energy. That's half or 0.5 mass times the velocity squared. In this case, the velocity square is simply x dot square plus y dot square plus z dot square. And then the potential energy is, well, I'm missing something. So this is not just a point mass, but the body has a rotational energy. So the rotational energy is actually half ix omega bx square plus iy omega by square plus ic omega. Okay, omega b. Okay, so here the important thing to know is the angular velocity is the inertias are expressed in the body frame. Inertia in the body frame. Okay, so most SolidWorks or any tool you use to design things will actually give you inertia in the body frame. What that means is that the inertia is about the axis. So let's say this is an object like this. So the inertias will be expressed in the frame, the X frame, the Y frame, the Z frame, as it is shown here. If you rotate the object to be in this configuration, okay, still the X would be this way, Y would be that way, and Z up. So and Z. So what happens in the body frame is that the inertia do not change. Okay, so inertia in body frame. So here the inertia is the same as the inertia in this frame because the body frame is attached to the body and rotates with the body. So that's the convenience of using body frame, is that these inertias are constant, they do not change as the body rotates. And that's why I wrote omega in the body frame. Okay, once we have that, we have to only write the potential energy, and I'm going to assume that, well, the object moves in the gravity is along the z direction. Okay, so mgz. Okay, where x, y, z are the position of the body in the, so maybe I need to make this clear. X, y, z is position in the fixed frame or the world frame, fixed or world frame. Okay, so that's the potential and the kinetic energy, and then I need to write the Lagrangian, which is T minus V. Okay, so most of the work is at this point done, and all that needs to be done now is to crank this through the Euler-Lagrange equation, which are d dt of dl dq dot j minus dl dqj equals to 0. In this case, since there are no forces, the right hand side is 0, or where qj is going to be all the state variables, so x, y, z, phi, theta, and psi. So 6 of them. So there will be, so these are 6 numbers, and then there will be 6 equations. Okay, once we solve for, well, we write the equations, we can actually compose them in this form. So we'll simplify the equations to look like this. A times, let's say, capital X equals B, where A would be a 6 times 6 matrix, and that's obtained when you take components which are in terms of, well, X is X double dot, Y double dot, C double dot, theta, sorry, phi double dot, theta double dot, psi double dot. So A is basically components which are linear in X double dot, Y double dot, and so on. And then B is also going to be a 6 times 1 matrix. and it's going to have everything which is not involving the acceleration. So it will have positions, x, y, z, theta, phi, psi, and velocities, x dot, y dot, z dot, and phi dot, theta dot, and psi dot. Okay, so what we'll do next time is I'll actually show you how to derive these equations. That is, put all these things we wrote down on paper into MATLAB, get the equations, then put them into to an ODE45 where we can integrate them, and then finally we'll do the animation. Okay, so work because it take me a while, and uh, I think this should be very self-explanatory if you have seen the way I've derived the equations for the simple planar cases, the two-link pendulum and so on. So first define a list of all symbolic variables which you will need. Okay, define the rotation matrices. This is essentially the way we express rotations, right? We have the 3-to-1 Euler representation, and this is just giving you a little bit more details on what exactly goes into deriving the equations for rotation. I already derived it in class. But once we have the rotation matrix, we can then find the angular velocity in the body frame. So angular velocity in body frame. Okay. Inertia is essentially in this case a diagonal matrix. So we assume that the body is nice and symmetric, and the principal axes are along the x, y, and z. And if that is not the case, then you want to accordingly modify the inertia matrix. If you have a CAD software, then actually the CAD software will tell you what the inertias are. So you can plug that in from whatever CAD software using to model the system. And then, of course, there's the velocity, uh, kinetic energy, which consists of two parts, the linear part and the part due to angular speeds or rotational kinetic energy. I actually like to write it this way, but if you want to write it as Vx square plus Vy square, that's fine too. This is just a shorthand way of writing the velocity. If you write the velocity as a vector, then this form basically gives you Vx square plus Vy square plus Vg square, and same for I omega square. Okay, and then the potential energy. So once we have that, then it's a matter of writing this equation, and really there's not much thinking here. It's just that you take that form which I wrote for two link manipulator and then just extend it to do all six links, right? All six variables. And so what comes out of that, and this is really doing some math to move things around so that I get that A and B matrix nicely. And so I wouldn't really expect you to understand this. If you want, you can, but you only would need to change these numbers to ensure that you are getting the right size A and B matrix. So let us run this. And this is actually some additional things which you not needed, but I just put it down there so that if you need it anytime, you can just copy paste it. So let's run this. Okay, so what you notice is that this kinetic energy is really long term. See this? Okay, and then it really makes more sense to use a package like symbolic toolbox in MATLAB to do it, because it's going to be very tedious to write the Euler-Lagrange equations by hand. In fact, this is actually a simpler system. Once I have like a system with multiple links, then this equation will be even more messier. So then the A matrix, which is going to be a 6x6, is produced, which is essentially writing each of the elements. I could have made it a little bit more compact, but it's easier to take this and paste it in the code, which I'll use to integrate the equation. So this is A and B matrix, and then all I need to do is find that acceleration, which is x double dot. And so then this part actually is what and you've done this for the Rimless wheel, I would copy, and then wherever I wrote the ordinary differential equations, the right hand side, the EOM, that's where I would paste it. This is copy pasted from running equations falling. That's it. That's the only part you need to paste. Okay, essentially the same thing. Okay, so let's go through this, which is basically initializing the system. You need to give a mass, inertia, gravity, and then this is just for animation. just for animation. There's nothing to do actually with the dynamics of the system. In fact, it's kind of interesting that length does not feature anywhere here in the equations, right? The length does figure out somewhere in the inertias, but since we wrote the inertia as ix, iy, iz, you don't really need to uh, consider these things in the equations, but they are needed when you want to animate the system. So then initialize the system. So I need to specify now um, I have 6 degrees of freedom, the 3 positions and 3 velocities. Sorry, 3 positions and 3 rotations. I need to specify the velocity counterpart, so which means I need to specify 6 numbers for linear parts, so positions and then velocities. And then for Euler angles, I need to specify them and then their rates. So there are 12 initial values I need to specify. Okay, and then there is the call to ODE45, which takes the equations of motion and integrates from time 0 to 1 second. Okay. This is very standard. I have some other things I put in here. You don't really need them. This is just checking if the total energy is conserved. If a system has no friction, no dissipation, the energy would be conserved. That's like checking if the equations are correct. This is all part, you can just ignore it if you want. I just put it there so that you have additional things if you need to use it for your homework. So let's just run this. So I'm going to run this again. Okay, so that's the block which is falling, and then there was a pause that was not because of anything but rendering of this thing in MATLAB. So once it produces the plot, it produces some graphs, and these graphs are, well, in this case, this is the x-axis time. In this case, the y-axis are the angular speeds. So there are 3 angular speeds for absolute angular velocity, and there are 3 for the body frame velocity, if you're interested in knowing them. There's nothing really interesting going on here except that I just plotted them and had calculations in the code to find what those are. As I said, the energy for a perfectly uh, non-dissipative system is conserved. So the total energy is in red, the kinetic energy, kinetic energy is red, potential energy is in blue, and the total energy, which is the sum of the two, is actually conserved. So that's like a check on the equations. And then I have the positions, the rotations, the rates for all those 12 numbers I talked about. So there's nothing really interesting here, just that I put that so that you have all that in one place. Let's run this again. Well, let me just actually change the initial value. So assume that I don't really spin anything, right? Everything is only has translation. So it's launched upwards with a velocity of 5 meters per second. And then what I would expect is the body will go up and fall down without any spin. Right? And this is sort of correlates with our experience of throwing an object. Now, if I spin it a little bit by some angle about, or put a spin along the x-axis, then I would see some spinning, but in this case, it looks like it's barely visible. So I'm going to ramp it up a little bit, 2.5. See what, or maybe 1. Yeah, it did spin. So you can see that the orientation did change. So that was spinning about x-axis. Now this is slightly hard to see. This is, if you did notice, it's probably the first time we're doing 3-dimensional figures. This is actually a 3-dimensional motion. So you can actually rotate it using this rotation tool to see the object. Now you can actually play with the view you want, and the command for that is in my code. It's actually called view somewhere in my animation. So if you see this view, that's the command used to change the view. So if you search for view, help view, okay, this doesn't give you what exactly, well, it tells you the definition, but I would just go to new. I'm going to open this same view in MATLAB. So view MATLAB, and that actually has a figure which actually explains what those two inputs are. View has an azimuth and elevation, and I believe there is a explanation for this somewhere in the down there. Okay, there it is. So this is how you're viewing the 3-dimensional object. The azimuth is the angle made with the positive y-axis, and the elevation is the angle made with the horizontal plane. Okay, so you can play with those to get the right view. In this case, I assume the azimuth to be minus, let's see, it's minus 42 and 0. And if you wanted a better view, the way I do it is instead of playing with those numbers, putting an azimuth in elevation, I actually do it this way. So let's say that I'm rotating it, okay? And you see that when I rotate it, it actually tells me the azimuth and elevation on the left, bottom left corner. I can't quite show you because if I let this go, then the elevation azimuth disappears. But you can see it on the left, uh, bottom left corner, azimuth is minus 15 and elevation is 41. So if you like this view, I would note that azimuth and elevation and then just put it here. So it's minus 15 and 42. So minus 15 and 42. And that's in degrees. So if you now run this code, it'll actually do the animation in this view. Let's run this. See, there it is. And then this plots many of these things are zero, so you don't see many variations here. But we can now change this, play with this a little bit. We'll change everything. So -2 and let's say +5. So things are going to spin like crazy in all directions. And then you can get a feel of it. Okay, so so that's about simulating simple objects, rather very simple objects in 3 dimensions.